All right, so we are on target 9D, and this is rates of change for linear and exponential functions. And as usual, let's start off with our learning goals. I can determine whether exponential or linear growth will produce a higher net result after a given amount of time. I can identify the difference between a linear and exponential function. I can identify whether a situation can be modeled by an exponential function. I can define the variables and write equations, both linear and exponential, given a real-world scenario, and finally use a table to extrapolate information regarding an exponentially modeled real-world scenario. That's a mouthful. All right, let's start off with the difference between linear and exponential functions. Okay, with linear functions, your y values increase by adding each time. So in this case, we're adding 2. Okay, and it increases by the same amount each time. With exponential functions, we increase by multiplying. Okay, so, and multiplying by the same number each time. So we're multiplying by 2 each time. I should note that this could also be subtraction. This could also be division. Sometimes you think with exponential functions, instead of division, we multiply by a fraction. But we'll get into that a little bit later on. Let's look at our first example. So suppose you won a contest at the Berwyn Town Center. For the prize, you start by winning $10, and the town agrees each month to either increase what you had the previous month by $75 or increase what you had the previous month by 75%. So we need to figure out which one is the best option. So increasing by 75% would give you the most money. Increasing by $75 would give you the most money. Money would be the same after 10 months. It's impossible to tell which deal would give you the most money, and increasing by 75% would give you less money than you started with. Let's start by eliminating the ones that we know it cannot be. We know for a fact it's not impossible to tell which deal will give you the most money. We can figure out one or the other, or both, which one will give us more money or if it'll be the same. So we can figure that out. So this last one here, we can cross that off. And then increasing by 75% would give you less money than you started with. Well, just by the fact that we're increasing tells us that we're not going to start off with less money, or we're not going to end up with less money. So we can eliminate those two. So let's figure out which one is actually true. So beginning with increasing what you had the previous month by $75, that's a linear function. And we can model that by saying we started with 10. We're going to add $75 each month. And we'll just say that that's f of m equals that. And then for our exponential function, we know it's exponential because it's got a percent. So we would write that as f of m equals, so we start with 10, times, now we're increasing by 75%, so that would be 1 plus 0.75 to the m, or 10 times 1.75 m. Okay, so we know that m is 10 because we want to know after 10 months which one would give us more. And I guess it doesn't say after 10 months, so we should say after 10 months. Okay, so the first one, 10 plus 75m, we replace m with 10, which is 10 plus 750, which is 760. Okay, so that's how much we would have by doing it that way. This, we have 10 times 1.75 to the 10th power, which when you put it in your calculator gives you, let's see, 10 times 1.75, $2,693.89. So obviously, this one's going to give you more money after 10 months. This isn't always going to give you more money. If this was after 1 month, for example, after 1 month, you'd have $85 with this as opposed to $1,750 with this. So it depends on how many months we're talking about. So let me clear all that off there. Okay, and so here's where it says which would give you the most money by month 10. So it was on there. So increasing by 75% would give you the most money. Second example, Use the two different tables of values to answer the questions below. Which table represents a linear function and which one represents an exponential function? So all we have to do is look and see which one is going up by adding, which one's going up by multiplying, or down, either way. So here we're adding 2 each time, so we're increasing by 2, so that one is a linear function. With this one, we're multiplying by 1/2, or you could say dividing by 2. Now, the way that we determine whether, as far as if you want to write it one way or the other, if you're dividing, what we do is we just say, okay, so if I want to write this as multiplication, I just take whatever I'm dividing by, I'm going to put that under 1 and say I'm multiplying. So that's how you would write it, as multiplication rather than division. But either way, we know that that's an exponential function. Next example, which situation can be modeled by an exponential function? Number of students attending Morton West increases by 35 each year. So each year we're adding 35. So that's not exponential. Flip phone sales at Verizon are decreasing by 375 per year. So that one we're subtracting 375 each year. So that one could not be modeled exponentially. Approximately 125,000 people enter the Willis Tower each day. That doesn't tell us anything. As the value of x increases by 1, the value of y increases by 6. So again, we're adding 6. Ford F-150 truck sales have been increasing by 3% daily. So there's that percent symbol. So that tells us that it can in fact be modeled exponentially. Okay, next example. As part of a biology project, Lewis is observing the growth of 2 plants. Plant A had an original height of 5 inches and is growing 1.7 inches per week. Plant B had an original height of 4 inches and its height is increasing by 45% each week. We need to define the variables and write a function that represents the growth of each plant. So your variables are going to be your y and your x, or your f of x and your x. So I'm going to use f of x since that's a little more appropriate. So f of x is the height of the plant. So basically when we solve our equation, that's going to give us the height of the plant at any given time. And x is the number of weeks because this is happening per week. So notice this is how many inches it's growing per week. This is how many, percent inches it's growing each week. So for plant A, we are adding 1.7 inches per week. So we have f of x, its starting height, 5 plus 1.7 inches, and that gets our variable. So that 1.7x, that's how many inches it's growing. X is the number of weeks plus the 5 inches that it originally started out at. Okay, for plant B, we have f of x. Its original height was 4 inches times how much it's growing. Now this 1.45, because it's growing, so it's increasing, that's 1 plus 0.45, because remember 45%, when we convert it to a decimal, is 0.45. So that's how we got this, and then x is our number of months, and that's an exponent. So again, remember to kind of raise that up and write it smaller. And that's all we need to do for that problem. And then finally, the following chart describes the growth of a colony of bacteria. Note that in 1 hour it grows from 2,000 bacteria to 128,000 bacteria. Use the chart to answer the questions below. So, does the chart model linear exponential growth? And explain your answer. So, I can say that because we are multiplying by 4 every 20 minutes, it's exponential growth. And that's exactly my explanation. Exponential growth because the number of bacteria is multiplied by 4. How long does it take the population to quadruple? So that's multiplying by 4. Well, it does that after 20 minutes, because notice 2,000 times 4. Each time it goes up by 4, by a factor of 4, is 20 minutes. So that would be our answer. And then how many bacteria will be in the colony after 2 hours? You can do this one of 2 ways. You can continue this chart so that we have 2 hours. Now keep in mind that this is time in minutes. All right, so we need to know that there's 120 minutes in 2 hours and go up by 20s until we get to that. And you can just take this last number and just keep multiplying by 4 if you want. But if it's something that would make this table a little bit, unruly, you can always write an equation too. So you could say f of x equals, we started with 2,000, we're going up by 4, and then x would be the number of time periods. In this case, how many sets of 20 minutes would it be? And in this case, we have 1, 2, 3, 4, 5, 6. So you could replace x with 6 and just do it that way. So if it's quicker for you to just write the equation, do 2,000 times 4 to the 6th power, and you're going to get 8,192,000 bacteria. So either way is fine. You can either continue the table or you can write the equation to get, the same answer. Doesn't matter. But make sure you do one of the two ways, because there's really not another way to do it. You do have options, but really only two at this point. Okay, so hopefully by now you are pros at exponents, both writing them and using them. And any questions you might have, please hunt me down, ask me in class, because if there's anything you're shaky on, it could affect the entire test, your entire understanding of all of this. So other than that, you guys have a wonderful day.